So we have a could be cast. That gives us a quick check whether what's happening could at least be a cast. And that is, something could be a cast if and only if everything between the left paren and the right paren could be a type, which is only if that's a type token. That's easy enough to do actually. We ask we do for int2 int peak level, peak amount, peak count, whatever, equals 2, while there is a peak and there we could use a comma expression. Where we do a peak of peak count. Then we put a comma on that. And then we have peak like that. And then we say peak count plus. I'm not sure if this will even compile. Well, only if you remove those things. Right. Well, that was compiled at least. So now we can say if first of all we grab the token type out here. By the way, this can be gone because the check we do right now is better. If we can actually just ask for peak token type. Because we know that this is not null. If peak token type equals paren, token paren, then we break. And we do this, or we start out with assuming this is true. If the token doesn't equal paren, we return false. If we hit the token paren, return result. We break, and then we do if token type is type token. If it's not a type token, we set result to false. And maybe we also break. Or we return false. And then the only way we could ever get here is returning true. And we don't need this boolean variable. And now the issue is that actually that only works if the peak 2 wasn't paren. So what we gotta do is we return I mean, this is a case just to filter out the things that can't be cast expressions. And this would return true on an empty pair of parens. But I mean, then there's that. Okay. So we ask, could this be a cast expression? if it could be a cast expression, we parse it as a cast expression. Well, and then, right, it can only be a cast expression if something follows it. So, int a equals z. That can't be a cast expression. But int a equals zx, that can be, because something follows it that's not a semicolon, not a comma. So only if the token after the right paren pause is not a punctuation token, so it is something that could be in an expression. Only then we are valid with our assumption that it could be a cast expression. And that would then also take care of the empty paren pair. So we say our paren count is 0, and when we encounter the paren, what we do is, instead of just breaking, we say paren count equals peak count. Right. And then we break. So now we can ask about the token. And if it is a punctuation token, then we can't have a cast. So now we can say if now that I'm thinking about it, I also would like to limit this loop. Where if we hit any amount of punctuation, we also want to break. What we could do is, and I'm leaning towards that more and more, introducing the cast keyword, rewriting our code to use the cast macro throughout, and then recognizing that, for now at least, so if we peek the thing after the operand count, yeah. So if there is no after paren, or the after paren is a punctuation token, in that case we return false. And then we can have a static bool, static inline bool with punctuation token, which is MetaC. Now, the punctuation token is or a dot dot or a comma. Or a semicolon. Everything that could be used to separate tokens. I think dot 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 comma semicolon arrow. Let's also talk every operator token plus minus type diff. What else can be punctuation? I think this is a good approximation of what can punctuate well, talk star isn't really it, nor is talk minus or plus, because then that can be in front of an expression. Like if you have a and minus c, that could still be a cast, could still be considered a cast, this and this as well, but for example this wouldn't be. So Takadan Tokaror would be one. Like that. I think this cuts out most of the invalid casts. And then we end up with things that can only reasonably be casts. When that is the case, what we do is we parse this thing as a cast expression, right? There is nothing else we can do. We have to do this. So we say result equals new expression, which is an exp cast, which, by the way, we have to add to here. We have exp call. After exp paren, there comes exp cast, like that. So we allocate a cast expression. Alright, what are we going to do next? Well, we have to match an paren . Let me think. Match it. Do we want to match it? Because if we match it, it becomes hard to go back and say, oops, we want to parse this thing as a thing. I'm now thinking about even storing all the tokens away. Such that when we discover, oops, this couldn't possibly have been a cast. Like, there are situations where you do int a equals b star c, where you could have a thing where b is a type of parent, or like unsigned, whatever. Right, and then equals whatever x, and x is an integer variable, like no, -1. Like, this would be completely valid, and this would be a cast, right? But it could also be that this is not the case, and this is not the case. Start with int c3 and int b2, and then this would be a regular 3 times 2 expression. So we can never be fully sure until we do semantic analysis how we should parse this type. We should parse this expression. Now, another option that we have is to not decide about what this is. We know this is some expression, some kind of expression. We could call this the undetermined karst expression. And all this thing does is store tokens. This is possible. Well, actually, the only way that this can be ambiguous is if the type consists of a single identifier. If it consists of anything else, like if it consists of a type keyword or of a star, right? Then it is determined that this is. It has to be a cast. It can only be parsed as a cast if it is that. Or it's invalid. So that means the only case in which we have to reverse what we think about this is when the type that we are parsing is a single identifier expression. In which case we always have the power to reverse. If we see a cast expression where the type is an identifier expression, and then we have a pointer expression of another identifier expression, which is what we have here. We have a type identifier, then we parse. This is being seen as a unary expression, which is then a putter deref, then putter exp of an identifier exp. That would be what is being built out of that. And we actually then have the information in the expression to recast this, to rebuild this as a multiply expression with identifier identifier C. So actually, if we are a bit careful, we can reverse this decision if it turns out that the decision to parse a cast here was wrong. So no worries about that. So what happens is we say result of type equals, let's call this cast type, equals parse parse a type declaration. Self, no parent, no previous, go. And then let's result at E2, like cast exp equals MetaC parser parse expression self export flags none, no previous. And I believe this would work. Yeah. So we match, we match. We're just peeking it right, so we match the paren. Then we match the top paren, and we just have to note that there is the possibility that this cast expression might not be a cast expression. There is one case in which it can be a multiply expression. One. Well, two, really, because you could parse the type. You could parse the type as a pointer type, and the other expression as an identifier expression. So I guess there are two ways in which we could parse a type expression, a multiply expression. Anything else? Anything else includes a binary subtraction, binary addition, so not a unary. And all of these of identifier expressions, right? Yeah, on the left hand side. So all of these are possible to fix up. It is possible to fix this up. If we got it wrong in the parser, we can fix this up. So no need to get too overly excited about things. What we now need to do is to go into our expression T and add the members that we would have in a cast expression where cast colon, and then we have structs. Come on. Struct like that. Where we have MetaC expression pointer first. Cast and Should I call it cast exp? I think call it cast exp. And meta C type a decal type T star cast type. I believe this is it. I'm just going to come on here. Peak count is undefined. Pretty sure I defined it up here. Oh, well. Let's look into that. So meta parse type. Does this one parse expressions? Yeah. This shouldn't be an exposed function via the header. Or I could leave it where it is and just do the pre-declaration in this file. Oh, come on. So it should tell me where it is previously implicitly declared. Just go above there, put a semicolon there, and we're done. Is punctuation token? I'm pretty sure I capitalize. So yeah, now if we have an expression such as E D we do it as a cast exp, right? Whereas E times D is a regular binary exp. So that's good. And of course we can get this one wrong, right? Which is why this is a could be cast expression. If we do this, E times A, right? This also becomes a cast. Because we don't know what E and A is, so we don't know that this could be this. Right? But we can fix this up in semantic. We can fix this up in semantic if it doesn't make any sense. Right? So, the important thing is that we mustn't get into the place where we trust this cast expression to always be a cast, right? We mustn't do that. what we should do now is teach our printer how to print cast expressions. Alright. Else if x kind equals x cast, we do print character print type print character probably want to do print token lparen and print token paren so we can do funny things with it, but for now what ifs. We can replace the print car with a left paren using a regex replace, so it's not like it's a big deal. And then we print expression self x cast x, it's cast type, not x type. Right. I believe that's it. We now have everything we need to print our cast expression, and you can see like how it binds, right? Because regular binary expression looks like this. But the cast, you can recognize that we are doing a cast like this by how it binds. And actually, the way this should bind is like this. So that means that the precedence of cast is not done correctly. We can, just to make it more explicit, say print string cast 4, so we can just put the cast keyword in when we print our stuff to make it more visible when we are parsing casts. This is cast E. Then we have a unary expression, which is star A. Let's just send us this, right? Right. And then we can say star A plus B, like that works. And the reason we have the parens here is because this shows that star is applied to A. So if we had like a star A plus B, oh, this is bad, because this is parsed wrongly. The way this should be parsed is like this. Oops. Oh. The issue that we now face here is that what we are just now trying to parse as a type is not a valid type. Oh no. Because the types have their stars, if there are pointers following the last non-star token, whereas in this case we see, oh, it's a paren, it could be a cast. Oh, it's a type token, could be a cast. Oh, it's a type token, could be a cast. Oh, there's not paren, still could be a cast. So let's try and parse this as a cast. And when we're trying to parse it as a cast, we are calling parse type decal. And parse type decal will complain about this not being a valid type expression. Right. So we need to be a bit more strict now. It could be cast, because I don't want to deal with crazy, not really valid types being handled in parse decal type because somebody thought it could be cast, when we can fix that in our could be cast function. Could be cast. We can just have another thing, star count equals 0, and whenever we discover a star, we set star count could say star pause. I think I would like pause better. So let's rename this one to pause. We call this one first star pause. or like if token type is star and peak count equals 3, then we know the first thing to see in there is a star, which means we are dereffing something, which also means return false. Cannot be a cast at that point. Right, now at least our parser doesn't crash anymore, so that's good. Let's sync our progress. Once the NFS starts again. And that is it for parsing cast expressions for now.